When we're working with balanced systems, we've seen that they typically have exactly one solution. But sometimes something goes wrong. Let's start by seeing the things that go wrong in systems with two equations and two variables, because the geometry of this situation is easier to see. The solution to a system of two equations in two variables represents the point of intersection of two lines. And this can go wrong in two different ways. The first way that this can go wrong is that we have two lines that don't intersect, as we do in this example. Here we have a pair of parallel lines. This line is the graph of equation 1. And this line is the graph of equation 2. The lines are parallel, so they don't intersect. This system has no solution. Now we can see that in the picture, but if we hadn't drawn the graphs, that might not be obvious. Let's see what happens if we try to solve a system like that algebraically. I'm going to use both substitution and elimination, just so we can see what happens in each case. This system is set up to make substitution fairly easy. One of my equations is already solved for y. So I'm going to plug 2 into 1, and I'll get 3x plus 2, y is equal to negative 3/2 x minus 1 equals 6. Distributing here, I've got 3x minus 3x minus 2 equals 6. When I combine like terms, I just get negative 2 equals 6. And that just isn't true. Let's see what happens if we try to use elimination. For elimination, I'm going to need to first put 2 in standard form. So I'll add 3/2 x to both sides. I'll multiply both sides by 2. So this is just equation 2 now in standard form. I'm going to multiply both sides of equation 1 by negative 1. That'll give me negative 3x minus 2y is negative 6. And when I add down the columns then, I get, well, 0 plus 0 equals negative 8. Okay, so clearly something has gone wrong here, because negative 2 does not equal 6. 0 does not equal negative 8. The equations that I ended up with contain no variables, and they're false. They're false statements about numbers. Okay, what's going on here? Well, we have these parallel lines that don't intersect. A system like this, where our lines don't intersect, where our equations have no shared solutions, is called inconsistent. Inconsistent, they can't both be true at the same time. These equations are inconsistent. One thing we'd like to notice, we'd like to be able to spot these right away without doing a bunch of algebra. And one thing we can notice is that in standard form, it's really obvious by looking that these are the equations of parallel lines, because we have a 3x and a 2y. So as long as we're planning to use elimination, and we put everything in standard form first, we can spot an inconsistent system right away, because we see that we have two parallel lines. That's going to be useful to us with the systems of three equations. Now, I said that two things could go wrong. What else could go wrong that would keep lines from intersecting at a point, other than being parallel lines? Well, take a look at this example. Looking at this example, you might be thinking, did I forget to graph one of the lines? And the answer is no, I didn't forget to graph one of those lines. When I actually graph these two lines, I get the same line. It turns out that those two equations are actually the equation of the same line, just written in different forms. These two equations' graphs are the same line. Now, when that happens, we have a system with infinitely many solutions. Namely, every point on the line is a solution to the system. Typically, we describe that by just saying everything that works in that equation is a solution to the system. And again, if we've actually drawn the graphs, this is obvious. What happens if we try to solve this algebraically rather than by looking at the graph? Again, I'm going to use both methods for this just so we can see what happens in both methods. This system is already set up to make substitution pretty easily. I'm going to plug equation 2 into 1. And I'll have 3x minus 4 times, according to equation 2, y is equal to 3/4 x minus 1. And that's all equal to 4. Now I'll distribute 3x minus 3x plus 4 equals 4. Combining like terms gives me just 4 equals 4. Well, that's better than what we saw before, right? 4 really does equal 4 at least. But we still don't have any variables. Let's see what happens in elimination. Again, for elimination, we're going to need to put our equation 2 in standard form first. So I'll subtract 3/4 x on both sides. And then I want to get the coefficient of x to be a positive integer. So I'll multiply both sides by -4. And remember that this was equation 2, just rewritten in standard form. And we've already noticed that something's wrong, right? Because that looks a lot like equation 1. In fact, it's exactly the same equation. But just to carry this through to its conclusion, I'll take -1 times equation 1, -3x plus 4y equals -4. And when I add those together, I get 0 plus 0 equals 0. Again, when we tried to solve this algebraically, we ended up with equations that contain no variables. But this time, well, 4 really does equal 4. This is true. 0 really does equal 0. This is also true. So we ended up with equations that contain no variables. But in this case, those equations are true. When that happens, that means that we're in this situation where we have infinitely many solutions. A system like this is called dependent. If you ask me if equation 1 is true, I can say it depends on whether equation 2 is true. They'll both be true at the same time. They depend on one another. Also notice, as we already did, that when we put both equations in standard form, it's really easy to tell by looking that they're the same line. To recognize in the previous example that those lines were parallel, we needed to know something. To recognize that those are the same line, we don't need to know anything. We can just see. Those are obviously the same equation. And again, being able to recognize that those are the same equation, well, for one thing, that's why we defined standard form the way that we did. But for another, being able to recognize that those are the same equation is going to make our lives a lot easier. Because once we see we have the same equation, we know that we have a dependent system, and we can stop doing algebra.